Welcome again to this presentation. Today we are discussing again the questions and answers regarding thermochemistry. Today we are starting on question 44. Question 44 is saying, calculate the change in internal energy for a system undergoing an endothermic process in which 15.6 kJ of heat flows and where 1.4 kJ of work is done on the system. Let's see the answer. Here we have the endothermic process. Endothermic process, that means the heat is absorbed, the heat is positive. With endothermic process, the heat is absorbed and we have the heat which is positive. That means the heat will be positive 15.6 kilojoule. Then you have also the work done. The work done, they are telling us that the work is done on the system. The work is done on the system. That means the surrounding is doing work on the system. The work is positive. Yeah, the work is done on the system. The work is positive 1.4 kilojoule. We know that the internal energy, the change in internal energy is equal to the heat plus the work done. That means it will be equal to 15.6 kilojoule plus 1.4 kilojoule. Then we will get 17 kilojoule. Here the heat is positive and the work done is positive. Then we get 17 kilojoule. The system has gained 17 kilojoule of energy because the energy is positive. That means the internal energy is positive. That means the system is gaining energy. If the internal energy becomes negative, that means the system is losing energy. Let's continue to question 45. Question 45 is saying ethane gas has a gamma ratio of 1.22. This is a gas which has a gamma ratio of 1.22. They are asking what is the molar heat capacity of this gas at constant volume and at constant pressure. That means here we need to calculate the CV, the molar heat capacity at constant volume, and the CP, the molar heat capacity at constant pressure. So we have derived the formula for calculating the CP. So this is the relationship between the CP and the CV. From this relationship between the CP and the CV, we can then get the formula for calculation of the CV. We know the relationship is that CP minus CV is equal to A. So that means if you can divide CV on both terms, here we can divide CP over CV. Here also we divide by CV. Here also we divide by CV. We get CP over CV minus CV over CV equal to R over CV. Then in this case, we know that the gamma is equal to CP over CV. So this is replaced by gamma. That means we get the gamma minus 1 equal to R, the gas constant, over CV. That means gamma minus 1 times Z, gamma minus 1 times CV is equal to the gas constant. We can get then the CV. CV is equal to the gas constant dividing with gamma minus 1. So we'll be using this formula to calculate the CV. CV is equal to gas constant dividing with gamma minus 1. The gas constant is equal to 8.3145 joule per mole Kelvin dividing with the gamma was given as 1.22 minus 1. Then we get here 37.79 joule per mole Kelvin of the CV, which is the molar heat capacity at constant volume. Let's determine also the molar heat capacity at constant pressure. We know that the gamma ratio is equal to CP over CV. Then this is the CP, which is the molar heat capacity at constant pressure. CP will be equal to gamma times CV. then Cp is equal to gamma times Cv. In this case, we can replace the values. Gamma ratio is equal to 1.22 times 37.79 joule per mole Kelvin, which is the Cv. Then we get 46.1 joule per mole Kelvin. Question 46, what is question 46 asking? 46 is saying we have to consider 4 moles of monatomic ID gas at 300 Kelvin. They are asking to calculate the internal energy of the gas. So we know the formula to calculate the internal energy. So the formula for calculating the internal energy is equal to NCVDT, or Du is equal to NCVDT. The internal energy is equal to NCVT. So here we have the temperature. We have the temperature which is equal to 300 Kelvin. We have the number of moles which is equal to 4 moles. Now we need to determine the CV. We have a monoatomic ID gas. What is the CV for monoatomic ID gas? How do we calculate the CV? Again, the CV is equal to this relationship between the degree of freedom and CV. We know that CV is equal to F, which is the degree of freedom, over 2 times the gas constant. The CV is equal to the degree of freedom dividing with 2 times the gas constant. So remember, this is the second formula to calculate the CV. The first one was the gas constant over gamma minus 1. The second one is CV is equal to the F, which is the degree of freedom dividing with 2 times the gas constant. For monatomic gas, we have seen that the degree of freedom is equal to 3. That means the monoatomic gas, they only have the translation motion, translation on X, translation on Y, and the translation on Z axis. They don't have the rotation and the vibration motions. The monatomic gas, they don't have any vibration and the vibration and rotation motion. They only have translation motion. They can be translated from X, Y, and Z. That's the reason why we are saying that they have the degree of freedom is equal to 3. So we can then calculate the CV. CV will be equal to 3, which is equal to degree of freedom over 2 times R. We get the CV is equal to 12.47. After getting the CV, then we can calculate the internal energy, which is equal to NCVT. 4 moles, the equation you have 4 moles times the CV that we have calculated times the temperature. Then we get this amount of internal energy. Question 47 is saying estimate the molar heat capacity of the following gas molecules at room temperature. It is asking to determine the molar heat capacity of helium and nitrogen at room temperature. So we use the formula for calculating the CV. CV is equal to F over 2 times Z, the gas constant. So we need to calculate for helium. Helium is monatomic gas. I told you that monoatomic gas, the degree of freedom is equal to 3 because they don't have the rotation and the vibration. They only have 3 translation motion, translation on X, Y, and Z. Here, then we can replace by 3 here. Then you calculate the CV for helium. CV for helium, we replace here by 3. Then we get this amount of CV. Then we calculate also for nitrogen. Nitrogen is the atomic gas. For the atomic gas, F is equal to 5 at room temperature. Temperature. So remember, the total degree of freedom is equal to 3 times N. If nitrogen has 2 atoms, nitrogen gas has the atomic molecule. That means the total degree of freedom it will be equal to 3 times 2, which is equal to 6. But here, because we are at the room temperature, we use only 5. At room temperature, only the translation motion and the rotation motion are active. No vibration motion are active at room temperature. That's why here we are using 5. So if you have the temperature which is around or less than 6 Kelvin, in this case we have only translation motion. When we are at room temperature, this is the temperature at room temperature between 300 Kelvin and 600 Kelvin. This case we have only translation and rotation motion. So here, because they are saying at room temperature, then we need to use 5, the translation motion plus rotation motion. And if they increase the temperature, the vibration motion are only reactive when you are having around 3000 Kelvin. Here we are using nitrogen is a diatomic gas. For a diatomic gas, F is equal to 5, the degree of freedom is equal to 5 at the room temperature. Here we are only counting the translation and the rotation degree free of freedom, and we are ignoring the vibration motion. Then we calculate the CV for nitrogen. We replace 5, the degree of freedom, over 2 times the gas constant. Then we get this amount of the CV. Let's move to question 48. Question 48 is asking a certain complex ideal gas molecule has 7 degrees of freedom. The degree of freedom was given as say 7. They are asking calculate the average translation kinetic energy of a single molecule at 300 Kelvin. Here they are asking to calculate the kinetic energy at 300 Kelvin. They are also saying determine the average translation kinetic energy for 3000 molecules. They are also asking to calculate the kinetic molecule for 5000 molecule. Then finally they are asking to calculate the molar heat capacity for this complex molecule. They are giving the Boltzmann constant, which is equal to this value. Now we need to calculate the kinetic energy. Let's see the answer. So we know that the internal energy is equal to kinetic energy plus potential energy, but for the ideal gas, because there is no interaction between molecules, the potential energy is equal to 0. So here for the ideal gas, the potential energy is equal to 0. That means the internal energy is equal to the kinetic energy. So this kinetic energy that they are asking, that we can calculate it. We can calculate it as the internal energy. Now we know that for internal energy is equal to the degree of freedom over 2. Because here we have the 7 degree of freedom, we need to use the formula to calculate the internal, relating the internal energy for the degree of freedom. Internal energy is equal to degree of freedom over 2 times PV, degree of freedom over 2 times nRT, or degree of freedom over 2 times nkBT. So we use this one that has the Boltzmann constant that was given in the question. That means the kinetic energy is equal to the internal energy is equal to F over 2 nkB delta T. Or here we are using the temperature because we have only the 300 Kelvin. Then we can progress and calculate the what is N. N is the number of molecules. In the first question they are asking determine the translation kinetic energy. Calculate the average translation kinetic energy for a single molecule. That means N will be equal to 1 for single molecule, and F is equal to 7. The degree of freedom you have say 7. N here is equal to 1. Degree of freedom is equal to 7. The Boltzmann constant was given, and the temperature was given as 300 Kelvin. You can replace the values F by 2, F by 7, 7 over 2, S by 7 over 2. This is the degree of freedom. The N is 1. This is the number of molecules. Then the Boltzmann constant, replace it, and the temperature. Then we get the kinetic energy that they are asking. So we go to the N. The N is equal to 5000. F is equal to 7. Then in this case we replace here 7. The N will be equal to 5000. The Boltzmann constant times the temperature, and we have the kinetic energy. They are also asking to calculate the CV. How do you calculate the CV? So remember the formula for calculating the CV is equal to F over 2 times the gas constant. The F was given as 7. So we replace then the value of the degree of freedom and the value of gas constant, and then we get 29.1 joule per mole Kelvin of as the CV. Question 49. Question 49 is asking what is the change in internal energy for 3 mole of argon gas if the temperature increases from this one. Here they are asking the internal energy, and we know the formula to calculate the internal energy. When we put the formula to calculate the internal energy, the change in internal energy is equal to N CVDT. Then here what do we have? We have 3 moles we have the change in temperature because they are saying the temperature increased from 300 Kelvin to 500 Kelvin. That means here you can get the change in temperature. We calculate the CV. Remember, we calculate the CV by having the degree of freedom dividing by 2 times the gas constant, and we have the argon, which is a monoatomic gas. For monoatomic gas, the degree of freedom is equal to 3. Then we can calculate first the CV. We calculate the CV. After calculating the CV, then we calculate the change in internal energy. Then we get this internal energy. Only to replace the value. So you need to understand that the internal energy is equal to NCV dt. The CV, which is the molar heat capacity at constant volume, is equal to F over 2R. Then the remaining one is to replace the values, and you get the answer. Question 50. Question 50 is saying, calculate the change in internal energy for 4 moles of nitrogen gas when the temperature decreases from 400 Kelvin to 300 Kelvin. So it's the same. So we are going to use the internal energy equal to, the change in internal energy is equal to NCV dt. The number of moles, you have 4 moles. The change in the temperature, we get them from here. Then you calculate the CV. CV is equal to F over 2R. We have nitrogen gas is a diatomic molecules. That means we need to consider that F is equal to 5 at this temperature. So we are given this temperature falls in this category. That means we are at room temperature. The degree of freedom which are active is only translation and the rotation motion, which are equal to 5. Here with this temperature, that is where only the vibration motion will be active, but we are here at 400 Kelvin and 300 Kelvin. That means we are having only F is equal to 5 as the degree of freedom. We can then calculate the CV. After calculating the CV, then we have the internal energy, which is equal to negative 8316 joule. So negative because you can see the temperature is decreasing. The internal energy is a function of temperature. If the temperature is increasing, the internal energy is positive. When the temperature is decreasing, the internal energy is negative. Question 51. Question 51 is saying, estimate the change in internal energy of 7 mole of gas with a gamma ratio of 1.3 if the temperature increases from this temperature to this temperature. So remember, we have seen the CV. When you have the gamma, then you can calculate also the change in internal energy. So what is the formula to calculate the change in internal energy? So you remember where? So this is the formula to calculate the CV when you are having the gamma ratio. CV is equal to gas constant divided by the gamma ratio. The gamma was given as 1.3. Then after replacing, you get the CV. After getting the CV, we use the formula to calculate the internal energy, which is equal to NCV dt. 7 moles. The CV was calculated by using this formula, gas constant over gamma minus 1. Then we get the change in the temperature. Then we are getting the internal energy, which is equal to positive. Positive because the temperature is increasing. I told you the internal energy is a function of temperature. If the internal energy is increasing, the temperature also increases. If the temperature is increasing, that means the internal energy is positive. Question 52. Question 52 is saying, compare the change in internal energy for 5 mole of monoatomic gas and 8 mole of diatomic gas if the temperature increased from 300 Kelvin to 500 Kelvin. So for monoatomic gas, the degree of freedom is 3, and for diatomic gas, the degree of freedom is 5, because here we are still at the temperature, which is room temperature. Then that means we need to calculate the CV. After calculating the CV for monoatomic gas, we calculate the CV for the atomic gas. After calculating the CV, then we calculate the internal energy and we compare the internal energy for the two gas. Here we have the internal energy is equal to NCV dt. The CV for monoatomic gas is equal to F over 2 times the gas constant. F is equal to 3 for monoatomic gas. For the atomic gas, F will be equal to 5. So we calculate the CV for monatomic, we get this value. We also calculate the CV for the atomic by replacing the F, then we get this value. Then we calculate the internal energy for monatomic gas, we get this value. We also calculate the internal energy for the atomic gas, we get this value. You can see that the diatomic gas has more internal energy as compared to monoatomic atomic gas. Let's see question 53. Question 53 is saying 800 joule of work was performed by a gas in a perfect insulated container. Insulated container, that means we are having a adiabatic process. Then 800 joule of work was performed. That means the system is performing the work. That means the work done is negative. They're asking how much heat energy was transferred. Here in adiabatic process, we don't have the transfer of heat. That means heat is equal to 0 or delta Q is equal to 0. What is the change in internal energy of the gas? So then during adiabatic process, because the heat is equal to 0, that means the internal energy is equal to the work done. The change in internal energy is equal to the change in the work done. Then they're asking, with the temperature increases or decreasing, that's where we are going to see the temperature increase when the internal energy is positive and the temperature decrease when the internal energy is negative. Let's see the answer. We have adiabatic process because they are saying it is a perfect insulated container. This is adiabatic. The heat is equal to 0. The delta Q is equal to 0. The work was performed by the gas. The work done is equal to negative 800 joule because it was performed by the gas. And then we know that the change in internal energy is equal to the heat plus work done, and the heat is equal to 0 in the adiabatic process. That means the change in internal energy is equal to the work done. So that means the du, the change in internal energy is equal to the work done, is equal to negative 800 joule. You can see that the internal energy is negative. That means the temperature is decreasing. The temperature is decreased because the internal energy is negative. Let's move to question 54. Question 54 is saying the temperature of 4 mole of NaO decreased from 500 Kelvin to 300 Kelvin during adiabatic expansion. We have adiabatic expansion. The temperature of 4 mole of NaO decreased from 500 Kelvin to 300 Kelvin during adiabatic expansion. Adiabatic expansion, the temperature is decreasing. Or adiabatic expansion, the temperature is decreasing. When you have an adiabatic compression, there is an increase in the temperature. Then they're asking how much heat energy was transferred. Because they have an adiabatic, there is no heat which is transferred. The heat is equal to 0, the delta Q is equal to 0. Then they're asking calculate the internal energy of the gas. We know that for a adiabatic process, internal energy is equal to the work done. They're asking how much work was performed during this process. So we know the internal energy, the formula, of course, adiabatic process, we have seen that Q is equal to 0. So, and then internal energy equal to NCVDT. Here then, internal energy is equal to the work done. After calculating the internal energy, immediately you get the work done. They're asking how much heat is equal to 0. They're asking calculate the internal energy is equal to NCVDT or is equal to the work done. Then they're asking calculate how much work. That means the work is equal to internal energy. The number of moles was given. We have 4 moles of NaO. NaO is a monoatomic gas. A monoatomic gas, they have the degree of freedom is equal to 3. Here we replace F by 3. 3 over 2 times the gas constant. After getting the CV, then you calculate the internal energy. Here we have the CV is equal to 3 over 2. We get the CV. After getting the CV, we calculate the internal energy. We have the change in temperature here. We see that the internal energy is negative. The internal energy is negative. The work done also should be negative. So because in a adiabatic process, the work done is equal to the internal energy. So the heat is 0. The work done is equal to the internal energy. That means the work done will be equal to the internal energy. Of course, you can see that here the internal energy is negative. The work done is negative because you have adiabatic expansion. When you have adiabatic compression, the work done is positive and internal energy is positive. Here also, what you need to know is that the temperature, when you have an expansion, the temperature is decreasing. Question 55 or question 55, it is saying nitrogen gas expands adiabatically. Nitrogen gas expands adiabatically from this volume is 0.02 meter cube at this pressure to 0.08 meter cube at this pressure. Then they're asking how much work was performed by this gas. Calculate the change in internal energy. They're asking how much work was performed. Calculate the change in internal energy, of course, because we have expansion, which is adiabatic. The internal energy is equal to the work done. But here we know that the internal energy is equal to NCVDT, and we don't have the change in temperature. We have the volume and the pressure. That means here we don't have the external pressure, which is constant. That means we have to use here reversible adiabatic expansion. That is the formula that we have to calculate, that we use. The formula that we use to calculate the work done. When you have the work done irreversible, you can use NCVDT. Here we cannot use this formula because we don't have the temperature in the equation. We can also use this CV over R, P2V2 minus P1V1. Of course, we have P2V2. We have it here, and we have P1V1, we have it here. We can determine the CV. So this formula, we can use it. Another formula that we use is this one, but because we don't have the gamma ratio, we cannot use this one. Here also, this also used for the reversible adiabatic process, but we don't have the temperatures. Here is used when you have in irreversible process. But irreversible process is when you have a constant external pressure or a single phase. Here they didn't mention that the work was done at a constant external pressure. You can see that the pressure is not at constant external pressure. That is the reason why we are using the reversible adiabatic process. If they told you that the expansion or compression has been done at a constant external pressure, in this case, you are going to use irreversible process. Reversible process occurs at constant external pressure. Then we use this one to calculate the work done, and we know the work done is equal to the internal energy in adiabatic process. So calculate the CV here. CV is equal to F over 2R. Nitrogen gas is a diatomic gas. F is equal to 5. That means we are going to use the degree of freedom is equal to 5. Then we get the CV. After getting the CV, we calculate the change in the work done is equal to CV over L. The P2V2 minus P1V1, you have it to replace the values. Then we get the work done in Pascal meter cube. So we change this Pascal. We put the formula for Pascal. What is a Pascal? 1 Pascal is equal to kilogram per meter second square. Then after replacing here the Pascal by kilogram per meter square, we get kilogram meter square per second square. Then that is equal to 1 joule. That means the dW, the work done, is equal to negative kilogram meter square times meter cube. Here we can meter and meter cube and meter, they get cancelled. We get kilogram meter square per second square. Then we get this is a joule. This is joule. In this case, then you have the work done, which is equal to this value, and delta Q, which is 0, and then du, which is internal energy. The change in internal energy is equal to the work done. Because the question they were asking to calculate the work done and internal energy. Because you have an expansion, that is the reason why you see the work done is negative and the internal energy is also negative. An expansion. When you have an expansion, the work done is negative. And the internal energy is negative. The temperature decreases during an expansion. Now let's move to question 56. 56 is saying air is compressed adiabatically. We are adiabatic compression from this volume to this volume. The pressure, you can see, times 10 power 5. The pressure also is changing. Air has a gamma ratio of 1.4. How much work was done on the gas? Again, here the pressure, we don't have external pressure, which is constant. We use also the work done for reversible, and the formula here, because we are having the gamma ratio, you can use this formula. we have the gamma ratio, and we have the pressure, the P2, V2, and P1, V1. Here we are using this formula to calculate the work done, which is reversible. How much work was done on the gas. In this case, then you can use the formula gamma ratio, which is 1.4. We replace the values, and then at the end you will see that we will get the value. Can you see here? We get this value for question 50C, question 56. Let's go to question 57. Question 57 is saying a car engine takes in air at 25 degrees Celsius and 1 atmosphere and compress it adiabatically. It is the adiabatic compression to 0.1 times the original volume. That means the original volume is V1 and the final volume is 0.1 times V1. There has a gamma ratio of 1.4. What is the final temperature and the final pressure? So here we will see the formula. Remember, we have derived the formula to calculate the final temperature and the final pressure when you have the adiabatic process. So here, of course, we don't have a constant external pressure. We have the reversible process. But here I'm going to show you the different formula that are used to calculate the final temperature and the final pressure when you are having the reversible and the irreversible process. But here in the question, we have the reversible process. For reversible process, we can use this formula to calculate the final temperature, or we can use this one to calculate the final pressure, or this one. Can use this one and this one to calculate the final pressure, and this is the first one is used to calculate the final temperature when you have reversible process. For irreversible process, you can use this formula. Either you can use this one, you can use this one to calculate the final temperature, you use this one to calculate the final temperature, or the last one to calculate the final pressure. So what you need to understand is that here, if you have the degree of freedom, you can use this one. If you have the gamma ratio, you can use this one. If you don't have the gamma ratio and degree of freedom, you can use this one to calculate the final temperature. So then let's use the first one for calculating the reversible process, the final temperature in reversible process, because this question you have reversible process, we don't have the constant external pressure, so then you have reversible constant external pressure. In this case, you use the formula for irreversible process, but here we have reversible. So we have the temperature, the T1, and we have the V1. This is the gamma minus 1. The gamma was given. We have also the T2 that we need to calculate. Then the V2 will be equal to 0.1 times V1. Then we replace also here the gamma minus 1. So we get T2, which is equal to 748.5 Kelvin. Then we can calculate the final pressure by using this formula. Then we have the P1, which is 1 atmosphere. We replace with V1 here. V2 will be equal to 0.1 times V1. Then in this case, we calculate the P2 is equal to 25 atmosphere. We have also another formula to calculate the P2. We can also use this one to calculate the P2. You also get the same answer of 25 atmosphere. You can see that we can calculate the final temperature and the final pressure by using the formula for reversible adiabatic process. Let's see question 58. Question 58 is saying we have 1 mole of monoatomic ID gas expand adiabatically at initial temperature of this one. The initial temperature was given against a constant external pressure. I told you when you have against a constant external pressure, in this case we have irreversible process from 1 liter to 2 liter. Find the final temperature of the gas. In this case, we are using the formula to calculate the final temperature for irreversible process. We have a constant external pressure. We have irreversible process. In irreversible process, we use this is the formula that we use to calculate the final temperature. You can use this one. You can use this one or this one. So then, in this case, what do we have? Do we have a gamma ratio? So we don't have. We have a monoatomic monoatomic gas. You can use NCV T2 minus T1 is equal to negative P external pressure V2 minus V1. External pressure we have it, which is equal to 1 atmosphere. The V2 we have it from 1 liter to 2 liter. That means V2 is 2 liter and the V1 is 1 liter. Then what do we have? Do we have the initial temperature? Yes, we have it 300 Kelvin initial temperature. We don't have the T2. Then the CV, because we know the monoatomic gas, we can calculate the CV. The number of mole, you have 1 mole. So we can again calculate the T2, find the final temperature. Can you replace the CV is equal F over 2 times R? Remember, for monoatomic gas, the CV is equal to 3 over 2 R, because the degree of freedom is equal to 3. Then we get the CV, the N is equal to 1. Then after getting the CV, we replace the value. N is equal to 1 mole. We replace the value for the CV. The T2 minus T1 was given. Then we determine the T2. What is the value for the T2? Then you get 291.88 Kelvin. So here we are using the formula for irreversible process because we have against a constant external pressure. We have also 59. Question 59. Question 59 is saying a sample of fluorocarbon was allowed to expand reversibly and adiabatically. You have a reversible process to twice of its volume. That's why here we are having V1 is equal to V1 and V2 is equal to 2 times V1. During its expansion, the temperature dropped from 400 Kelvin to 100 Kelvin. The temperature decreased. Here we have the change in temperature. Assuming the ideal gas condition, we calculate the CV of the gas. Here we need to calculate the CV for the gas, but we have also the reversible expansion. Now let's see the formula that we use to calculate the CV. Remember, the CV is equal to gas constant divided with gamma minus 1. Here we don't have the degree of freedom. That's why we are using this formula. CV is equal to gas constant over gamma ratio minus 1. What we don't have, so we don't have the gamma, we can calculate the gamma ratio. Calculating the gamma ratio from the final temperature or final pressure. So the formula to calculate the final temperature or the final pressure, we can use them to calculate this gamma ratio. We have P1 and P2, we don't have. We have T1 and T2. So you can use then this formula to calculate the gamma ratio. After getting the gamma ratio, then we replace the gamma ratio to calculate the CV. Here we replace T1 was given, T2 was given. Then we need to calculate the CV. We replace the 400K V gamma minus 1 to 2V, because we are told the V2 is twice the initial volume, 2V. Then in this case, we have 400K over, we are putting this one, 2V over gamma minus 1. Here, then we cancel, get 4. 4 equal to this one, 2 gamma minus 1 times V gamma minus 1 is the same as 2 gamma minus 1 times V gamma minus 1, dividing with V gamma minus 1. So then you have here V gamma minus 1, V gamma minus 1, they cancel. We get 4 equal to 2 gamma minus 1, then 2 power 2 equal to 2 gamma minus 1, then here the 2 they cancel. We can say that gamma minus 1 is equal to 2, then gamma equal to 3. After getting the gamma, then we replace the gamma here, then we get the CV is equal to R over gamma minus 1. We get the value of CV that was asked. We have also question 60. Question 60 is saying a system with 2 mole of an ideal gas at 300 Kelvin expand adiabatically in a single stage. So here we have a single stage. If it is in a single stage, that means we have irreversible adiabatic process. Because a reversible adiabatic process, initial, there is an equilibrium between initial and the final stage. So we don't have a single stage. In this case, you have irreversible adiabatic process. Consider that the ideal gas is with a gamma ratio of 1.33. The gamma ratio was given, and during an expansion, the pressure decreased from 10 atmosphere to 1 atmosphere. So we have the 10 atmosphere and the 1 atmosphere. The final pressure, initial pressure, calculate the work done by the system. In this case, we are going to use the formula to calculate the work done for irreversible process. This is the formula to calculate the work done for irreversible process, which is equal to N times the gas constant times the constant external pressure T1 over P1 minus T2 over P2. What do we have? We do not have the external pressure. But in expansion, the piston will stop when the external pressure is equal to the P2. You have an expansion. That means at the end of expansion, the P2, the final pressure, is equal to the external pressure. So that means here we can assume that the P2 is equal to the external pressure. That means what is the P2? Because we have during expansion, the pressure decreased. During expansion, the pressure decreased from 10 atm to 1 atmosphere, 10 atmosphere to 1 atmosphere. That means this is the final pressure, and this is also the external pressure, because the expansion occurs and the expansion is stopped, the piston is stopped when the P2, the final pressure, is equal to the external pressure. So that means the pressure external pressure is equal to P2 is equal to 1 atmosphere. So then you have the T1. T1 was given. Yes, we have in either gas at 300 Kelvin. We don't have the T2. P1 we have it as 10 atmosphere. P2 we have 1 atmosphere. External pressure is equal to P2 is equal to 1 atmosphere. The gas constant, you can find it there. The number of moles you have it is 2 moles, but you don't have the T2. Then you can calculate the T2. What is the formula to calculate the T2 for irreversible process? In this case, you can use this NCV T2 minus T1. Then you calculate the T2. Now we have 2 moles of NID gas expand, but we are having here this formula again, T2 minus T1 over gamma minus 1, because we have the gamma ratio. Here we cannot use this one, but we use this one because we have T2 minus T1 was given. We need to calculate the T2. Gamma ratio was given as 1.33 minus 1. The external pressure is the 1. Then the P1, P2 was given. Then we can calculate the T2. This one we cannot use it because we don't have the degree of freedom. So we are using this one because we have the gamma ratio. So here we are in irreversible adiabatic process. Irreversible adiabatic process, these are the formula that we use to calculate the final temperature in irreversible adiabatic process. But we need to choose the formula in which you have data. This is where we have data. We have the gamma ratio. Here we don't have the degree of freedom. We cannot use this one. Here also we cannot use this one. Or here this also is possible. You can use this one. But the problem is that we don't have the V2 and the V1. Let's use this one to calculate the T2. After getting the T2, then we will calculate the work done by replacing the T2 and the other values, because we need to calculate the work done. So this is the formula. We are calculating T2. So we replace T1 by value, the gamma ratio by value, the external pressure. Then we calculate the T2. So we see that after rearranging, you will see that the T2 is equal to 233 Kelvin. So we are replacing and calculate the T2. Then after getting the T2, we calculate the work done by replacing the N, the number of moles, 2 moles, the gas constant, the external pressure, the T1, the P1, and the T2 and the P2. Then in this case, we get the work done, which is equal to this value. The work done in irreversible process. Let's see question 61. Question 61. Maybe you can end on this question today. Then the next time we continue with question 62. Question 61 is saying 1 mole of gas A with a molar heat capacity of 24.94 joule per mole Kelvin was mixed in the same container with 2 more of gas B. So they are mixing 2 gases, one with 1 more, another one with 2 more, with different molar heat capacity. The 2 gases expanded adiabatically and reversible. We have a reversible expansion, reversible adiabatic expansion from 1 liter to 4 liter. There we have given the V1 and the V2 and the T1. Starting at this one, here we can calculate the T2, then you have then calculate the work done by the mixture during expansion in calorie. Here they ask me to calculate the work done in calorie. We have reversible. So here, what we do, we need to make sure that we use the combined moles. That means the total mole will be equal to 2 plus 1 mole, which will be equal to 3 mole. Then we need to use the combined the CV. The molar heat capacity, we need to combine them. We need to see what is the formula that we use to combine to calculate the combined molar heat capacity. Other formula, we need to calculate the work done. What are the formula to calculate the work done? You remember, these are the formula. This is the first one, the formula to calculate the work done in reversible. The second formula, the third one, the fourth one, and then we can choose the one in which you have the data. Do we have a T2 and T1? Yes, T1 we have it, T2 we can calculate. The CV, we can calculate the combined CV, the number of mole. We are going to use the combined number of mole. So this is the formula CV of gas mixture. That is how we calculate the combined CV. You take the N1, the number of mole of gas 1, times the CV of gas 1, plus the number of mole of gas 2, times the CV of gas 2, dividing with the number of mole of gas 1 plus the number of mole of gas 2. Okay, here then what we don't have the T2. How do we calculate the T2 for reversible process? Remember, we use this formula. This is the formula. This is the second formula. This is the third formula. But we need to calculate here the T2. You can use this one because we have a V1 and V2. We have also the gamma ratio. We have the gamma ratio here. The work done by mixture during expansion. Let's see. Here we can calculate the gamma ratio. Then we have here 1 plus 2. This is the combined CV. After getting the combined CV, we can calculate the CP and CV. So we have the combined CV. After getting the combined CV, we can calculate the CP by taking CP is equal to R plus CV. Then after getting the CP, we can calculate the gamma which is equal to CP divided by CV. Then we get the gamma ratio which is 1.5. The CV, the combined CV, you need to calculate the combined CP. Then after you calculate the gamma. After getting the gamma, then you can use the formula above to look for the T2. T1 V1 equal to T2 V2. Here the gamma we get them. Then we can calculate the T2. So you will see that the T2 will be equal to 160 Kelvin. So only we are replacing the values. The T1, here the V1 and the V2. This is the gamma ratio that we have calculated. The trick here is to calculate the gamma ratio by using the combined CV and using the combined CP. After getting the T2, then we need to calculate the work done is reversible, which is equal to NCV T2 minus T1. The T2 was calculated as 160 Kelvin. The T1 you have it, the N you have it, and the CV we have it. Then we can replace the value 3 moles. The CV that was calculated, the combined CV. The CV is here, the combined CV. Then the change in temperature, and then you get the work done in joule. But you need to convert to calorie by dividing with 4.184 joule per calorie. Then you get this amount of work done in calorie. The work done in reversible process in calorie.